Welcome to my YouTube channel. This is my new YouTube channel, and I have just decided to actually post a series of lectures on chemistry. And I do believe that there is a language like math that is central to science. There is a language that is central to chemistry as well, and that's the language of Lewis structures, and then at a higher level, language of structural formulas that is applicable to organic chemistry. That is my profession. So if you're following this, we're going to start with Lewis structures, letting you know how to draw any molecules Lewis structure. So we need two tools. The first set of tools is called Lewis dot structures, with these elements from group 1 arranged to group 8 noble gases. So with group 1 we have 1 electron, 2 electron, all the way to 8. There are 4 spaces unseen, invisible spaces around each element that we could clearly see them in carbon, that there are 4 of them, because in each of them there is 1 electron, so we could see. And in these 4 spaces there are orbitals. We don't actually draw them, but we'll talk about them later on. For main group elements, there's 4 of these orbitals for the valence shell, and each orbital occupies 2 electrons, so maximum number could be the gases, the noble gases, that has 8 electrons. And all the efforts of elements to make molecules, Lewis structures so to speak, is to make it to 8 electron in their valence shell. Okay, so go 1, 2, 3, 4, and there the electrons just occupy this next empty space around it until it reaches 4, and then electrons start to pair up. These single electrons, we call them single reacting electrons, and those are the ones that are going to be shared and make bonds. The one that are pairs of electrons, we call them lone pairs. And why do you call them lone pairs? Because they're reluctant to react. And for xenon, if you notice, that's group 8. We call group 8 noble gases because they have all around them lone pairs, and so that's why they don't actually want to react or are reluctant to react, and that's why we call them noble gases. So this is the first tool, the Lewis dot structures. And then when we draw a Lewis structure, we count the number of lone pairs around the central atom, and then the surrounding atoms around that central atom, and then we add them up to actually work out a geometry or a framework. I have actually models of those all geometries here, and it could be a linear geometry, it could be a trigonal planar geometry, a tetrahedral geometry, a trigonal bipyramidal geometry, and a octahedral geometry. Okay, and for all these geometries you could have different number of lone pairs. So these are the frameworks. Basically, they are not specific to any molecule, but they could show you, they're the pathway to show you which kind of geometry each molecule gets. I'm going to use the models to very quickly show you how these work. For the linear framework, you could have 2 geometries. One of them is, if you have 0 lone pair, that would be the same, called linear, and that's the same for all the other frameworks. If you have 0 lone pairs, the name of the geometry would be the same as the framework itself. And if you have 1 lone pair, it's going to occupy this space, so I just detach one of those to get also a linear geometry. And you could have no more than 1 lone pair in a linear geometry. For trigonal planar, there are 3 spaces in the framework. You could have no lone pair. Again, the molecule geometry would be trigonal planar if there's no lone pair. It could be also 1 lone pair that gives you a bent geometry. Okay, so that's trigonal planar, or the bent geometry. For tetrahedral, there could be no lone pair, but the framework itself would, the geometry would also be as the framework tetrahedral. There could be 1 lone pair, so I detached them and it gave me a pyramidal geometry. For the molecule, there could be 2 lone pairs, and I detach one another, and it gives me a bent geometry. Okay, for the trigonal bipyramidal, if you could see the ones that are the one that are top and bottom, these 2, and actually are called axials, and those that form a plane, like these 3 that form in a plane how to say, a plane, that are in a planar position. These are called equatorials, and the lone pair for this geometry always go to this. It means you could always detach this, but not the actual, not the top and the bottom one. They would always be here. So there could be no lone pair, which gave you the trigonal planar itself. There could be one lone pair that gives you sort of a seesaw structure, so we call it the seesaw, as you can see. There could be two lone pairs and give you a T-shaped structure, so to speak. And there could be also three lone pairs that gives you back a linear geometry. For the hexagonal octahedral geometry, there is also the possibility of two lone pairs maximum, because lone pairs could always be on the actual position. So there is a planar position here, and then one top, one in the bottom. If there's no lone pair, again the geometry is octahedral itself. If there's one lone pair, we call it a square pyramidal, because it's like a pyramid, and in the base there is a square. And if there's two lone pair, we call it the square planar, because it's a square again, and it's kind of planar. Okay, so let's go talk about specific examples. I'll start with water, which is the simplest, most ubiquitous compound in our, at least in our planet Earth, and it's what gives rise to life. So water is very important. It's very simple, but it's kind of also has many mysteries around water and the chemistry of water. Okay, so water has H2O, that's the formula. Okay, and there is an oxygen, group 6, that's the central atom. Central atoms are mostly those that have maximum number of single reacting electrons, and there's a hydrogen here, there's another hydrogen here, and hydrogen have usually one single reacting electrons, and hydrogen is the only element that needs only 2 electrons in its valence shell to actually feel satisfied. Others also always need 8. That's why we called octet. We have a rule called octet rule. That means every element other than hydrogen needs 8 electrons in its valence shell to feel satisfied. If I share these electrons, the single reacting electrons that we talked about, you could have 2 bonds, and when you do so, hydrogen is satisfied here, this hydrogen is satisfied. When you do this for the second hydrogen, oxygen also feels 8 electrons in its valence shell. So I could essentially say, okay, I have 2 bonds here, and then I count 2 lone pairs, 2 surrounding atoms, and there's 4 is this one here, also this geometry. Because I have 2 lone pairs, I'm going to detach 2 of this to give me a bent geometry. That's the geometry of water molecule. Okay, I could also go on and try to draw. You don't need to do the framework as I'm doing here. I always do this, because I'm going to show you the exact way how you do this, but you don't need to do that. So H2O is a bent geometry. You could see that I don't put the lone pairs here or here on the corners, because lone pairs do not possess shape. That's also the same reason why I actually detach this, because lone pairs do not have shape. So that's the bent geometry, and you could put it in a framework of a tetrahedral, and a tetrahedral with 2 lone pairs, as we speak earlier, it's called bent. Okay, so that's this. Let's go to yet another molecule, the NH3. Okay, so NH3, nitrogen is group 8, my bad, group 5, so it has 3 single reacting electrons, 3 hydrogens in the molecule, because it's NH3, and I'm going to share the single reacting electrons of each hydrogen with the single reacting electrons of the nitrogen. That makes 3 covalent bonding. And if I do so, you could see hydrogens are going to be satisfied one by one. And as I do the third hydrogen, the nitrogen is also going to feel exactly 8 electrons around its valence shell. So it's satisfied through the octet rule. Okay, so I can then say, okay, there are 3 bonds, and then the lone pair is just 1 around my central atom, and the surrounding atoms are the 3 hydrogens, so it's 4 again. But this time, the tetrahedral framework that I have, if it has only 1 lone pair, let's try to see what I could say. what I could have. So this is the tetrahedral geometry framework. If I just detach one for the one lone pair that I have, I will get a pyramidal geometry overall. Okay, so that's the pyramidal geometry that I have, and then I'm going to also rewrite real quick so that you can see how this pyramidal geometry could be drawn on a 2D paper. Again, you don't have to draw this green framework unless you're very interested and enthusiastic about chemistry like I am. Okay, so there are these three bonds, and then on the top, again, the lone pair doesn't go to the corner, and that's the exact reason why we detach this from the top. Okay, let's go to yet another molecule, the CH4. Methane is known as the marsh gas, and it's also been famously reputed that Auguste Kekule used to have models of 3D models of methane. Auguste Kekule, by the way, is one of the most prominent chemists of his time, and he is famed to actually have kept 3D models of methane molecules. So methane carbon group 4, it's this configuration. There are 4 hydrogen atoms, and I could see that I have 4 single reacting electrons on my carbon, 4 single reacting electrons for the 4 hydrogens, and if I share them one by one, you could see that it would actually, as I do so, hydrogens would be satisfied as I do share the 4th single reacting electron with my carbon, or on my carbon with the hydrogen. It will also not only satisfy this 4th hydrogen, but it will satisfy carbon at the very end. So that's why we have this structure kind of stabilized. There is no lone pair around my central atom, and there are 4 surrounding atoms, 0 plus 4, again 4. This time you have the tetrahedral framework, but with 0 lone pairs, okay? So if there's 0 lone pairs, it means this is the same geometry, the geometry of a perfect tetrahedral. That's the geometry of methane, and that's the model that Auguste Kekule, as I talked, used to keep in his office. Or at least it's being told that he used to actually have this model of methane, 3D model of methane being kept in his room. Auguste Kekule is also the one responsible for the very famously responsible in organic chemistry for the discovery of the structure of benzene. We may talk about the structure of benzene later on in this series of lectures. So that's the methane. You could see that there are 4 positions in each and the corner of the tetrahedral. Let's now move to some examples that are very simple molecules, diatomic molecules. For the diatomic molecules, the strange thing or the easy thing about them is that they never have to go even to the level of complexity of a linear molecule. Because if you have a linear geometry or framework, you have to have a central atom and 2 surrounding atoms. When you have a diatomic molecule, there's only 2 atoms, so you can't say them which one is a central and which one is a surrounding. Okay, we'll start from the very simplest one, H2. Hydrogen. Hydrogen again is an exception. Hydrogen is the most ubiquitous, the most abundant element in our universe, the cosmos, the whole universe, and it's the only one in the only exception in our periodic table that only needs 2 electrons in its valence shell to actually feel satisfied, and that's because of the structure or the configuration of helium. Helium is a closed shell molecule. We'll talk about this later on, but you only have to remember hydrogen with only 2 electrons, it would feel satisfied. So if I just share these 2 electrons, it's just one bond between the 2. Always diatomic molecules would be linear, okay, because there's no other geometry. If you have 2 atoms, they could be only closer or further from one another. There's no other choice for the geometry. The geometry is going to always be linear. Let's talk about the gas that is ubiquitous in our atmosphere, N2, the nitrogen. Nitrogen is group 5. I apologize. So if we share the first single reacting electrons, now each nitrogen has only 6 electron in its valence shell. If we share the second one, each nitrogen now have it has now 7, yeah. And then when we share the third one, each nitrogen would feel 8 electrons, these 6 and these 2 here, and these 6 and these 2 here, because these are shared, so both nitrogen actually feel them. And there are sort of a three covalent bond between them. We call this triple bond. We have double bonds and triple bonds other than single bonds, and we'll talk about their properties later on, but for now it's only enough to know that it's very strong. When you go multiple bonds, double bonds are stronger than single, and triple bonds are more stronger than double bonds. So that's why nitrogen is so hard to rip off, to actually detach, and we have a special bacteria called nitrogen fixators that can actually rip off this molecule. It's also known that when you have lightning bolts can also rip off an N2 molecule. O2 is the gas that we breathe. It's easier to break it down. It's group 6, so it has this kind of configuration. When you share the first pair of single reacting electrons, you would have, on each oxygen you would have only 7, and when you share the second single reacting electrons, you now have 8 electrons around each of those oxygens, and we could actually say there is a double bond between the two oxygens. That's the structure of oxygen. That's easier to break than N2. And now I'm going to go to a series of halogens. I'm not going to draw all of them, but you're going to actually see that they're going to be the exact same. So fluorine, chlorine, bromine, and iodine, they all form diatomic molecules. For I just do F2, F is group 7. And if you just replace the F for chlorine or bromine or iodine, that would be the same exact structure, okay? So fluorine has 7 electrons, and it only has one single reacting electron, so if I just share this one, each fluorine would now have 8 electrons in its valence shell, and there is a single bond between the two. That's the case for chlorine, iodine, bromine. I could just delete this to do chlorine, or bromine, or iodine. These are all diatomic molecules, and they have one single bonds between them. Okay, I'm going to wrap up here for the first session, and we'll continue on the structure of more complicated Lewis structures.